All right, before the break, we were starting to talk about some hardware components. This is an introduction class, so sort of introducing the terminology here. I often do refer to this class as a vocabulary class. I try to do it as like hands-on learning stuff, and when we're doing hardware in the classroom, a lot of that vocabulary is like, okay, it's a CPU is this piece, and actually pointing at motherboard and stuff. And I have a couple to look at on Thursday after we talk about all of it today, but really that's going to be a picture. It's not quite the same on the Zoom call as when we're in the classroom opening up the machines, but it's an intro level, so we're just starting here. Just the terminology, the names of the pieces in the computer. There's one other picture I like to draw before I erase all this and move on to the next section related to CPU. We have our control unit, and those are core instructions, the ROM built into the machine, a clock to synchronize everything, and a counter to keep track of which step we're on. RAM, which is separate from our CPU, but our CPU could not work without the RAM, and the RAM would be a chunk of silicon, which if y'all are used to seeing the black plastic, the silicon is like glass. If you look at the chemical composition for it, it's the actual silicon we're using to do stuff on the machine is very similar to glass. So you're probably used to seeing those black pieces, and that's just a protective plastic. We usually wrap them in black protective plastic that has to do with heat dissipation. We'll talk about that before long. The reason they're always black is just to make sure the heat spreads nicely. Some of y'all may have noticed that before. If you're walking through a parking lot on a hot day, it's hotter if you're standing next to a black vehicle than next to a white vehicle. Or if you touch a metal car hood, the black ones are hotter than white ones. That's why they're all black. If you cut those open, you'll see like a clearish purple squishy plastic stuff inside. That's the silicon. So when we put those together, we have all these different ones. The RAM would just be that squishy silicon substance if it wasn't connected to a CPU, and the CPU couldn't do anything without RAM connected to it. That's why I always like to draw them together. The registers are usually inside of the CPU, and that's RAM holds the whole program, registers hold the current step. So there's sort of a flow as things go through here. I'm going to leave those pictures of registers up for like the next thing we're going to talk about. But sort of generalizing this picture here, I'm going to start with input because that's probably what we're usually thinking about. We make some input to the machine, a bunch of stuff happens, then we get the output at the end. And as we go through here, the first thing our input devices do is map to the control unit. Got out of room there. When they go to the control unit, and then the control unit moves into RAM to grab whatever the appropriate instruction is. So all of the buttons on your keyboard, they're mapped to a specific spot on the control unit. So when you push a button, it knows what to go grab, where to go in the control unit, and that'll correspond to something stored over in RAM. So grab that information, and from there, it goes to either our floating point unit. I should stop drawing the boxes first because I keep running out of room. Or the arithmetic logic unit, depending on which one we're going to process stuff with. And then from there into the registers. And then the register will sort of be connected to the control unit to make a comparison to see when that instruction is done. Because it might need to come back around and go through those processing steps again. And when it's finally done, it will come out to the output. And the important thing I wanted to note here is our input, the hardware itself, will get pushed onto the control unit. Backwards. Sorry, backwards. That gets pulled onto the control unit. So it's like sitting there constantly listening for that. And when it detects it, it like pulls that number in, then pushes it out to RAM. Which then pushes it onto the FPUs, and the registers kind of pull it from there. I'm using those terms loosely to indicate the thing I wanted to indicate there is the registers are able to push something back out. They're storing stuff, so the registers and the RAM, those are the pieces that can push stuff. They're storing stuff so they can activate a switch and send that stuff they're storing output. So that's what's meant by push. And here where I say pull, like the FPU and the ALU, all they're doing is sitting there, and when something gets pushed out, they take that in. And then up here, the control unit's just sitting there, and when something happens on the hardware, it's able to take that in. So it's like a spot for it to fall into. Those obviously aren't official terms. I like to bring them up in introduction classes to help get a picture of what's going on here. And then likewise, our register pushes things to the output, or the output pulls things from the register, because the register is what can actively do stuff, and the output's just sitting there waiting for something else to happen. I like to put that on there. The big thing, those aren't technical terms. It's just how kind of picture this is some pieces actively do things, and other pieces are passively sitting there, waiting for something to happen. The control unit actively flips a switch and sends the output to the RAM. And likewise, the RAM, a switch is activated and things are actively sent to the next step. Whereas the ALU and the FPU, they're always passive. They're just sitting there doing their stuff, doing their thing whenever stuff comes to them. So there is a mix of active and passive units there. They aren't all constantly doing something. For those continuing on in the long run, keep that in mind that some of the pieces just sit there and other pieces activate and deactivate. And as they do so, the electricity flows on to the other one, which is a segue to the next thing we're going to talk about. So that's just a really rough picture. If that's the sort of level you're interested in, there is a great picture on Wikipedia. If you look up, well, I'll point at it. If that's the level you're interested in, a good place to start, there's a picture on Wikipedia that is a step above that one I just drew, but still below schematics. So you're not looking at electrical schematics, but more detailed than that one I just threw up there on the board really quick. I think I just looked for CPU and on Wikipedia. Oh, that's going to sell ads. CPU Wikipedia. Yeah, so they have a picture on here that is a little more detailed than that. That will help get you a good starting point if that's what you're interested in. Okay, yeah, this picture right over here. So you can see the different pieces in our central processing unit and how things flow from the input back and forth between those pieces and active and passive parts, and then finally to the output. So if that's where your interest lies, the Wikipedia page is a good place to get to get started looking into that a little more in depth. But how our electricity flows. It's okay if I erase that quick picture. It's just a very rough sketch.
Yeah.
Not even technical terms there. Just something to try and help introduce this. Yeah. It's an introduction class, trying to get everybody off on the right foot for when you get into those classes that have all the really advanced technical terms, where you're just exhausted all the time from all the trying to pick up all the terminology and make sense of it at once. So make sure we have a good foundation to move into that stuff in this class. So talking about electricity flowing through things. Oh, I'm gonna go ahead and erase this picture. Because that CPU needs to connect to stuff, right? So the second big piece I was going to talk about is going to be the bus, or a bus. We have multiple buses. So it's an important concept. The definition of it is a communication system that transfers data. System. That transfers data. So if you just suddenly pause and thought, that definition sounds like a wire, right? Well, a wire is a type of bus. We probably wouldn't use the term bus if we're talking about a wire. We use that for the more specific ones, but that is something that transfers data inside of and between computers, between components. Between computers and components. For us today, our conversation today is mostly about components. I think 2 weeks from now, we'll be talking about networks. So then we're going to talk about buses between computers. The basic concept is just the communication system to transfer data. There's different ways. And I left these pictures up here. For our registers, we have two main ways that we can load data into or get it out of a register. And we can have a single line going in, shift our bits over as they come, and then bring them out all at once. Or we can have a whole bunch of lines going in at once, and either a bunch of lines coming out or a single line coming out. We have that mix between a single line or a bunch of lines. And our terms for that are going to be serial and parallel. And basically serial means everything goes down one wire. Which, a quick little note here, usually when we try to represent serial transmission pictorially, we're going to draw one wire and we're going to write a bunch of bits on it, right? Like 0, 1, 1, 0, 0, 1, 0, 1. And we'll show all the bits flowing down that wire. But that is a pictorial representation. It's one wire, so it's like your light switch on the wall. It's on or it's off. And then the whole length of that wire is on or off, right? There's electricity all the way down the wire, or there's no electricity on that wire to control like a light switching grid. So serial communication is like that. And when we draw it this way, and we set up a time for it. So like maybe every nanosecond, just for an easy one, every nanosecond there's a different bit. So when we draw it this way, each one of those we're looking at a different nanosecond, and then both the things connected at both ends of that wire know that it's a different bit every nanosecond. So back to that synchronizing the clock to tell when things come down. So yeah, so it's like the light switch on the wall. It's all or nothing, but that doesn't make for a good representation when we're trying to talk about things and make sense of them. So it's usually drawn this way, but all the bits going down one wire. All bits on one wire. And parallel is sort of like each bit gets its own wire. Each bit its own wire. And since it's hard to draw things on the board here, I'm not going to try to draw a 64-bit one. I'll just draw like a 4-bit or something. So if we needed to transfer 4 bits, I'll put 4-bit serial. So we'd usually write it like that, 4 bits going down the wire. But in parallel, each bit would get its own wire. So 0, 1, 1, 0. And we can transfer a lot of data very quickly that way. And typically, you probably shouldn't have to think very hard about this to realize it. This is going to be a lot easier to plug up, right? If we're talking about external devices, if we need to plug something else up, it's a whole lot easier to plug in one wire than a whole bunch of wires. So usually serial communication is external to the machine, and internal to the machine on the motherboard. Haven't described that word, but I think most people have probably heard it before. So like on the motherboard, where that stuff's laid out in the factory and they can really easily put a whole bunch of wires next to each other, that's usually going to be parallel communication. So going from between the pieces on the motherboard, which, did I skip over that in my notes? It might have been on the previous page of the notes. Already drifted off of those. So that's the circuit board, the printed circuit board that we use to connect all of the internal components and connect all the electrical stuff. And internally, it's a lot easier to lay multiple wires out in a factory. So internal stuff is usually parallel, and external stuff is serial, which y'all are probably well aware of, because nowadays we plug most things up with on the universal serial bus, right? Our USB, that wire, universal, everything's kind of somewhat standardized. Right? Standardization means there's 10 different standardization competing, but all are different USB ports for micro and mini and USB-A and USB-C and all the different versions of USB is a universal serial bus. So you're probably should be familiar with some of those terms already, but they'll be important as we move forward. And usually if we're drawing a bus, like I said with wires, technically a wire fits that definition, but if we're going to use the word bus, we're talking about something more. So like our diagrams, we might see that as a really big arrow instead of just a thin line. Or a really big arrow to indicate that's a major communication channel, not just one of the basic ones. What does terms got here? RAM and ROM, I already talked about those. Oh, so there's a bunch of electrical components there. But while we're still inside, there's another thing we need to take into consideration. I mentioned it briefly just a moment ago with the reason that the chips we're used to looking at are all the same color. Right? We don't open up a computer and see a bunch of different colors, right? The printed circuit board that everything's attached to, that's usually in green. The reason for that is because it's easier on the eyes. The actual color of the material that's used is sort of a yellow milky stuff. Let me see if I can find a picture of it. Look for early PCBs, early PCB. And there's probably some pictures here. Yeah, so it's like this brownish yellowish color is the material we're actually using. But the thing is that they figured out really, really quickly that natural color hurts people's eyes. That yellowish, brownish mixes of yellows and browns. When the electrical engineers are staring at those circuit boards very, very closely for long periods of time, it actually damages their eyes. And y'all have probably noticed that most of the natural world, because of all the plants, is green. So our eyes can deal with green stuff a lot better. So that's why circuit boards are usually in green, so it doesn't hurt our eyes. And then most of the components we put on there, well, silicon is the same thing that glass is made out of, which glass is very clear, and in the form we use it in computers, it's still kind of clear. It's sort of a milky, clearish color. You could look through it, but it's not like glass. It's kind of distorted, maybe a little bit of purplish. But when you look at the board, everything's, all the pieces are black. And that's just a protective coating. And we're talking about electricity, right? Every place I wrote 0 and 1 here, that's turning the machine on or turning the machine off. And you all have probably seen it before just in life, that turning your machines on, they get kind of hot at times, right? The heat adds up, or sometimes after running something for a while, if you go to unplug it, you'll notice that that plug has gotten really, really hot. So if we're dealing with a lot of electricity, we need to worry about heat dissipation. Is it okay if I erase all this?
Yes.
That's the next major hardware thing that we always have to take into consideration. Something for heat dissipation. Which in our modern world, we'll probably use a lot of heat sinks and fans. So a heat sink is just a chunk of metal. Metal conducts heat very well. So we make a chunk of metal with, so we have like a circuit board. We want something, lots of surface area. So we have this little, some chip like this, and it starts to get hot. The heat might radiate out a little bit from it, but most of the heat is happening inside that block. So we need a better way to get that off, get that heat off of there. So a heat sink is like a chunk of metal we would put on here with a whole bunch of separate little fins. I'll try to draw it like that. Then we have a whole bunch of these little metal plates that aren't very thick, very, very, very thin things. So they have more surface area than internal area. And then there's lots and lots of space for the heat to dissipate from that. In our modern world, you've seen that in a lot of places, right? Like on radiators and air conditioners and all sorts of things. We always have those thin metal vents where there's lots and lots of little thin metal plates that the air moves past. And that just because it gives us more surface area than internal area, so more heat is able to escape quickly. Then to that, we usually have fans to move that around. Still coming back into some liquid cool stuff, liquid cooled, which is radiator. We don't use that word much anymore, but liquids can absorb a lot of heat, especially water. Water can take in it's just a physical property of it. It can take in lots and lots and lots of energy. You'll have probably noticed that before. Whenever you go to boil water to cook dinner, right? We have to turn that. We have to produce a lot of heat to heat up a small chunk of water. Right? The little burner on the stove is about the same thing we would put in a space heater to heat an entire room if we were to heat air. But when we want to heat water, like to make a pot of spaghetti, we have to turn that on and leave it running for quite a while. So water will take in a lot of energy, and then we can use that to get rid of heat pretty quickly. That's what always had to be done in the early days. Y'all have probably heard it said that the early computers were the size of a house. Actually, computers were never really much bigger than a desk. At the biggest, they were like an office desk. But the radiators to cool them down was the size of a house. It's really, really easy to heat things up and turn switches on. But cooling things down is a lot more trouble. So that's another important hardware component that always needs to be taken into consideration is how do we cool it off after we do stuff with all that electricity? Because it's naturally going to produce heat. It's 2:37. Okay, yep, we're on track. So just listing off all the things we need. Heat sinks and fans are the most common. And even when we get into the liquid cooled stuff, you'll still see a lot of heat sinks because it can pull that surface area can move things into air or liquid, moves the heat around more effectively than if we didn't have it there. This last big part of hardware for today is that's all. I just talked about a bunch of internal stuff, right? Some of the main things on the motherboard. Oh, we need a power supply. I'll talk about that after the next section. Still need a power supply, but let's talk about pieces on internal to the machine. Sealed up inside that case where we never really mess with it. Definitely not input and output devices. So in hardware, we're also going to have a lot of peripheral devices. And that's the outside things we plug in. Our inputs and outputs, mostly. Long-term storage. Would be a peripheral device. I mean, our hard drives are usually built into the machine in that same case that the motherboard holding the CPU and the main bus and the registers and RAM. It's in the same case as all that, but it is a separate piece. So by peripheral, back to the vocab nature of this class, when we say peripheral devices, that doesn't necessarily mean outside of the machine, it's outside of the motherboard. The things that aren't immediately soldered onto the motherboard for permanent attachments. And yeah, then that leads to this little picture I wanted to draw here. So we have that internal stuff, the sort of the motherboard itself, with a bunch of pieces. So we have our CPU in there. Oops. Our CPU, bunch of RAM, that's going to be an important one. Connect those together with some bus. Then a lot of registers. I'll draw them like this or something. And I'm just going to label one of those bubbles. So there's not much room in it. But the registers to accompany RAM, which again would be connected with some sort of bus, tying everything together. Which would be the wires built into the printed circuit board. And then we solder the pieces on top of them. Then we're going to need something for heat dissipation. I'm just going to try to draw a little fan in the picture here. little fan to cool everything off. And then all that would be connected into our main board, or the fan might just be somewhere near the main board. It's very common that when you open up a computer and look inside it, there'll be a small fan right there on the motherboard and then a bigger fan elsewhere in the system to help make sure everything's kept cool. And then we connect our peripheral devices. So coming off one of the registers might come over here to a monitor. That's a good picture for a monitor. That kind of looks like a monitor. I'll label it though. One of our main peripheral output devices, or coming out of RAM on like a smaller bus over to our long-term storage. Long-term storage. So a disk drive or a solid state drive, something to keep the stuff around after we shut the power off. So RAM and registers, when we turn the power off, they're going to lose all the memory. One of these registers over here might connect out to a NIC card. I'll just throw that out. I'll draw like the Wi-Fi signal or an Ethernet plug. That doesn't quite look like a plug, but our network connections, the Ethernet or Wi-Fi or Bluetooth, or however we're connecting to another device. Maybe this register goes over to our keyboard. So not super detailed today, but just kind of going over all the pieces and how they interact with each other and connect. Where's another? I don't like I've connected anything to this. So that, then we have our mouse. So sort of our primary inputs, our primary output, storing it. Those are all peripheral devices. Even if they're included in that same case that we have. Form factor would be the technical term for that. The form factor of the machine, is it a desktop tower or a clamshell laptop or a tablet? I think the word slate also shows up for tablets sometimes. I've seen that in textbooks. I've seen the word slate used, but I don't think I've ever heard anybody refer to a slate as, or a tablet as a slate shape, but they write that in tech. I've seen that in textbooks. And then clamshells like a laptop. It opens and closes, kind of looks like a clam, or desktop tower and separate peripheral devices. Because the last thing we need is, these are all electrical components, so we need a way to bring that in. So last main thing we'll need would be a power supply. I'll try to draw something that looks like a power supply. Oh, that picture didn't come out so well. I was trying to draw something that looked like a plug. Power supply, a way to bring power in, which usually has some adjustments in there as well. The typical home in America, 110 volts of alternating current running at 60 hertz. But all of these things that I was talking about up to that point all run off direct current. We use alternating current because it works much better for transmitting over long distances. But when we actually do stuff with our electricity, as far as component wise, direct current is much better, where it just goes in one direction, and alternating current switches to the direction it flows constantly. That's getting into electrical stuff, but usually in a home in America, we're going to have 110 volts of alternating current running at 60 hertz, and we need to switch that to direct current without any, and lose that frequency that it flips at. So all of that stuff is usually built into the power supply. All the ways to step our voltages down to the size we need, because most pieces run off, don't need much electricity at all. We plug into the wall that has 110 volts, but we need a lot less than that. So like I jotted down some notes. So my laptop, which when I wrote these notes was actually a couple laptops ago. I think my current one's smaller, but it requires 20 volts of direct current as opposed to the 110 volts of alternating current that comes out of the wall. So as that big box halfway down the cable that converts the alternating current to direct current and steps it down to the right size. Or tablets and phones use 5 volts of direct current. And then once it's inside, it still needs to step down again. Most of those internal components are going to run off 1.2 or 3.3 volts these days. There's still some things using 5 volts, but we have to bring the power to the right level of what we need. So there's a big separate component for that. Lots and lots of hardware pieces, just kind of listing out the names of them today. So you've heard them before. I think most people. Okay, yeah, I was kind of paying attention to the chat room. It's pointed out that the CPUs are often made out of copper or gold. You'll see gold on a CPU as well. A lot of people, yeah, gold has really good properties for that, even better than copper. So, and since it's very, very small amounts in a computer, you'll see that a lot more than you would say in a house. We use copper because it's cheap. Gold's actually much, much better for it. Sorry, I got a little distracted. Oh, yes. So going over the names, I believe another course that almost everybody has to take, or has to take at least one course of on your way through your IT program, is going to be an ITSP course, the IT support. And there you will go over all the hardware stuff in great detail. And it's a hands-on class, very hands-on class where you're taking machines apart and putting them back together. They use simulators for it these days, which isn't quite the same. Hands-on's a lot more fun than the simulators, I think. Everybody will see that. So just kind of introducing some stuff. I have a few more things to talk about with hardware on Thursday, just some scattered points, things you might see, especially moving into the future, because academia moves slow. If you haven't noticed that, academia tends to trail the working industry because it takes a while to put classes together. So sometimes might be a little bit behind where the industry is, talking about things from a few years ago, but a lot of our core foundation is still there. So introducing things in this class, does anybody have any questions about any of those terms we talked about today?
Not right now.
Nope.
Okay, so on Thursday, I'm gonna do a few other things, have a few things in mind it'll have to be pictures and video, but we'll do a little bit more than just talk about the words and draw pictures on the boards. But introducing things, terms that you all will hear a lot. Maybe you've heard those abbreviations a lot already. Computers are very integrated in our society. But that was kind of the list for today. Very much a talking day, just a bunch of terms to go over. We'll have some stuff to do. There's a hardware lab, and for the lab this week, you're gonna pull up the list of all the hardware components on your machine and get the details about what those are and tell me where you found them at. So there's more than one place, and I want to make sure that you're well aware of where you found it so you can get back to it when you need to get to it. Otherwise, that was about it for today. I know a couple people had questions. If you want to stick around afterwards, we'll address the questions. Does anybody have any questions before we wrap up, though?
No, sir.
So that'll be it for today. I will see y'all on Thursday and hopefully have something more interesting. What I have in mind is hopefully a little more interesting than a bunch of words written on the board. So we'll see that on Thursday. Y'all have a good afternoon. If you have any questions, let me know. And I'll see you then.
Hey, I have a question.